Let's prove a special case of Stokes theorem. So let's suppose, for the sake of this proof, that S is given by the graph of some function f over domain D. So in terms of this assumption, what we have is we have our surface S floating around in three-dimensional space, but we're going to assume that this is given by, like I said, the graph of a function where the domain now lives downstairs. So this is what I've actually drawn here is like the boundary curve C of the domain D, and we have a function, and this function is mapping this entire domain up to the surface S. So here's our function f, and our graph up here, our surface, is the graph of f over D. Now the way I've drawn it this way is because we need to make sure that in this scenario that the boundary curve of the function, so the boundary curve of the domain down below, has to map up to the boundary curve upstairs. And if the orientation downstairs is this way, the orientation upstairs is also the same way. Okay, and so then D itself is the interior of this region, and D maps up to the interior of the surface up above. All right, so these are our assumptions for the sake of this proof of Stokes theorem. So the other thing that we assume is that we have a vector field f, and f is defined on the surface, so on some domain that contains the surface, but it's at least defined on the surface. And f has component functions p, q, and r. And part of the assumption of Stokes theorem is that these p, q, and r have continuous first partial derivatives. So I'll just say continuous first partials here. All right, so that's going to be important moving forward. Let's also assume a couple other things before we get too far into this is moving forward. Let's assume that our boundary curve downstairs is parametrized. Okay, so let's say that C, the curve downstairs, C, is parametrized by a vector function, r of t, that gives it this proper positive orientation. So r is equal to x of t, comma, y of t, downstairs. And then what we know then, of course, is that z can also be written as a function of t now, because the z coordinate upstairs, when we try to parameterize the boundary, the image of the boundary curve, this is given by f of xy, of course, right, because it's the graph of a function. But along the boundary upstairs, so the boundary of S, the z coordinate is then given by f of x of t, comma, y of t. All right, so you just plug in the parameterization to get the z value. And let's just say, for the sake, again, of argument, that the interval that this is defined on is a finite interval from a to b. It should always be finite, but from a to b we'll say. So we'll give these things some names. Now what we want to do is we want to prove Stokes theorem in this special case. So we should first write down Stokes theorem before we try to prove it, right? So Stokes theorem says that the path integral around the boundary of the surface, so that's around the boundary of S, of f dotted with dr, okay, that this has got to be equal to, or this should be equal to, the theorem says that it is equal to, so be careful how we say this, right? But it is equal to the double integral over the entire surface S of what? Of the curl of f, the curl of this vector field f dotted with ds. All right, and let's remember how we compute a surface integral of this form. This is a flux integral. It's a flux of a curl, but to compute this flux, one way to do it is if we know the parameter domain downstairs, we can compute the double integral over the parameter domain. And in this case, the parameter domain is just the domain of the function itself, right? And so this is going to be the double integral over d of the curl of f evaluated on the parameter domain. So just evaluated over x and y. So in other words, we need to make the same substitution, z equals f of xy, in our curl vector field, dotted with normal vector. So the normal vector is also a function of x and y, right? dA. Okay? So let's do this. Let's start by computing the curl of our vector field and then writing out a formula for this double integral here. So one thing we need to do is we need to write down, I've already used r to represent the boundary curve, right? So I want to use something else now. So let me use, let's just call it omega, okay? So omega of x and y, this is going to be parametric function that it's going to be our function, right? But it's going to be thought of as a parametric vector function that defines the surface. So this is just going to be x, y, and then f of xy. So the z component is f of xy. This is exactly what we've talked about on our boundary curve, but this makes sense on the entire surface, right? And if we want to compute this normal vector nu, which we absolutely do want to compute this normal vector nu, then what we have to do is take the partial derivatives of this. And we did this in a previous section, but it's always good to review. So the x partial derivative of this parametric function omega is 1, 0. Remember, x and y are independent. And then df dx. Okay? The y partial derivative is just going to be 0, 1, and then df dy. And then what this tells us is if we take the cross product, then nu, our normal vector, is going to be the vector whose components are negative df dx in the first component. Just take the cross product here. In the second component, negative df dy. And the third component is 1. Now you might remember this. We worked this out, right? This formula is not new to us, even though its name is new. There's a pun there. But this is not new. We've worked this out before. But it's good, if you don't remember, it's good to work it out, right? And so what we need to do now, the next thing we need to do, is we need to write out the formula for the curl. So again, if you don't remember the formula for the curl, we have to write that out as well. But I'm just going to write the formula for the curl. So the curl of our vector field f, let's remember, f, this is f of x, y, and z, right? This is equal to p, q, r. So there's our p, q, r component functions, right? And so the curl of this vector field is equal to the vector field whose components are dr, dy, minus dq, dz. Okay, then it's dp, dz. Again, if you don't remember this, work it out. dp dz minus dr dx, and then finally, the last one is dq dx minus dp dy. Okay, and for this formula to make sense, it has to be p, q, r in this order of the components, right? So our surface integral, so the surface integral over S of the curl of f dot ds is going to be the double integral over the domain D, the domain in the xy plane, of the dot product of these two. So that's a function, right? So that's a dot product. And let's write it out. And by the way, this f, remember, our z is equal to f of xy, right? So it might be helpful for us to write dz dx and dz dy for these components. And so what we get is the double integral of our curl of f dotted with the s. This is a flux, right? This is computed as the double integral over the domain D of what? It's going to be, I'm going to use brackets because we need to take the dot product here, right? So this is going to be minus dr dy minus dq dz all times dz dx minus, same thing, right? dp dz minus dr by dx times dz dy, if you just swap out the z with the f for z, like we talked about. And then finally, it's going to be plus this term, right? dq dx minus dp dy. And then this whole thing is integrated up with respect to area. I'm going to put a box around this, and we're going to come back to this later. Because the next part of the proof is for us to compute the path integral, okay? Try to find a formula, work out the path integral, and hopefully get the same formula back, okay? So we have already talked about how to parameterize the boundary curve with respect to this vector function r. So this is our boundary curve parameterization right here. And so what we want to do then is write out a formula for the path integral and then kind of apply some chain rules, and of course you probably guessed it, we're going to apply Green's theorem down here. So let's see what happens here. So again, let's a little break here. We want to compute path integral around the boundary curve. This is the boundary of S. All right, so boundary curve ds of f dotted with dr, where our r is going to be equal to the vector function. We talked about this. X of t, y of t, and then z of t. I'm just going to write it out like this, but remember that z is a function of x and y at this point, right? And so dr is the vector function. X dot of t, y dot of t, z dot of t times dt. Okay, and we can just write out our path integral as f dotted with r dot dt. This is r dot right here, right? This is r dot. And so our path integral around the boundary of S of f dotted with dr is equal to the integral from a to b, that's the parameter domain for the boundary curve, of f, so p, q, r, dotted with x dot, y dot, z dot, dt. All right, and then when we write this out, we end up with integral from a to b of p dx dt, right, that's what x dot means, plus q dy dt plus r dz dt, all integrated up dt here. But then remember that z is a function, z depends on x and y, right? And so we can apply the chain rule. So the chain rule, you might remember that, I'm sure you remember this from chapter 14 of our text. So the chain rule says that if z depends on x and y, then dz by dt is equal to dz by dx times dx dt plus dz dy times dy dt. Okay, that's just the chain rule that we learned in chapter 14. And when we do this, we can write this out. This becomes the integral from a to b of p dx dt plus q dy dt plus r times, substitute all this in, right, dz dx dt. You can see what's going to happen here. We're going to regroup this. dz dy times dy dt, all still integrated up dt. And if we then rearrange this, right, then this can, so we're going to group this by dx dt and by dy dt, and we're going to group these terms together. So this integral now looks like the integral from a to b. The first term is going to be p plus r dz dx, all times dx dt, right? All times dx dt. And then it's going to be plus q plus r dz dy, all times dy dt. And this whole thing's integrated up with respect to t. At this point, we can kind of distribute back through. I know this is seeming a little bit convoluted, right? But we can distribute back through the dt to each of these terms. And remember that dx by dt times dt is just dx, right? In terms of differentials, they kind of cancel. Same thing with dy. And our path integral can now be written as the integral from a to b. We have to be careful now. If we get rid of the t component here, we have to just say, okay, this is just the path around the boundary of S, right? That was what our path integral was over. But this is now going to be the path integral of this. So p plus r dz dx times dx plus q plus r dz dy times dy. All right? And this one is a Green's theorem. By the way, we got everything, so this is no longer over ds. So I have to be more careful here. So I wrote down the a, b for the boundaries, but look what we've done. We've gotten everything in terms of just x and y. So all of this work that we did when we first wrote out this theorem here, right? And then we got everything else in terms of all the z's out of here in terms of just x and y. Then all of these are now living and working downstairs on the domain D. And so actually this path integral that we have after all this work, after this reduction, is the boundary curve of D in the xy plane. Everything here depends on just x and y. We've plugged in here to get this all in terms of x and y. And so this integral here is over C. And the reason that that's important, right, is because now that we're on this region in the xy plane, now Green's theorem applies. Right? And so we can apply Green's theorem to this to turn this path integral into a double integral over our domain D. All right? And so at this point, now we can apply Green's theorem. And this should not be a surprise, right? Because remember, Stokes' theorem is supposed to be a generalization of Green's theorem. And in this case, it's very obvious how that generalization works, okay? So by Green's theorem, what's this going to be, right? Well, think about this. This is now what we've got here. This is like the P and the Q. I'm going to give these hats just so we don't mess them up. The P and the Q of Green's theorem. So this is a F dot dr where this F is P hat and Q hat. All right, and Green's theorem says that then this path integral can be computed as a double integral over the parameter domain D up above, right, of what? dq bar dx minus dp bar dy. dp bar dy, all integrated up with respect to a, and we can write this out now. So this then becomes double integral over d of dq bar dx. Well, that's going to be d by dx of this whole thing, right? q plus r dz dy minus d by dy of p plus r dz by dx. This whole thing integrated up with respect to area. At this point, what we have to do is take these derivatives, multiply them out, and then when we're done, we'll go back up and compare with what we have up here. But when we take these derivatives, we have to be extremely careful because we have to remember that the component functions, p, q, and r, these are all functions of, x, y, and z. Okay, and so we have to be careful here because the other thing that's happening is that z is a function of x and y. So there's a lot of chain rules that we have to make sure we obey when we take these derivatives. And let's do it. I'm going to give myself a lot of room here. So there's double integral over d of now. When the derivative hits the x, the q here, then we take the derivative. So the chain rule is going to be dq dx dx dx, right? But then it's also going to have a term dq dz times dz dx because of the chain rule, right? Because the z component depends on x as well as q itself, right? So this ends up giving us dq dx plus dq dz times dz dx. That's just the first term. Plus, now we have the same situation with r, except that the z dy itself also depends on x. So this is a product rule as well, right? So this one gives us what? It gives us the r dx. So I'll write this in parentheses. dr dx plus dr dz times dz dx, all times dz dy, plus r times dz dy. Sorry, this is the second derivative now, right? So this is the second derivative, d squared z dx dy. All right, so this is all the first derivative of, this is the derivative of the first term, sorry, and then we need to subtract off the y derivative here. This one's going to be a little quicker for us because we kind of have an idea what's going to happen, right? So this is going to be dp dy plus dp dz dz dy plus, same thing with the r, right? So dr dy plus dr dz dz dy, all times dz dx, and then plus, okay, I'm running out of room here. Let me try to get some more room. I only need a little bit more, right? So plus, this last term is going to be d squared z, this is going to, times r, right? R, d squared z, this is now dy dx, and all of this is integrated up with respect to area. And all we have left to do now is combine like terms, kind of simplify through this whole thing, and see what's going to cancel, what's still going to be here, etc. So this becomes a double integral over d. A couple things definitely cancel. This term, r times d squared z dx dy, that term is in both places and there's a minus, right? So those are gone. By the way, it's not necessarily in both places, but our function f must obey in this scenario. I'm not sure I said it now, or before, but now it's going to be quite evident, right, that the second partial derivatives of f must obey Clairaut's theorem, okay? So f of x, y, z must have continuous second partial derivatives. All right, and so there's an assumption on the surface. The surface has to obey that. So as long as that's true, then these are equal by Clairaut's theorem, and they are obviously then going to subtract out. The other terms that are going to be equal are still involving r, right? dr dz, dz dx, dz dy. dr dz, dz dy, dz dx. So this term is gone with this term as well for the same reason. That time you don't even need Clairaut's theorem, right? Because that's not a second derivative. That's a product of first derivatives. And so finally, if we work all this out, we end up with dq dx plus dq dz times dz dx plus, this last term here is dr dx times dz dy, and then minus dp dy minus dp dz dz dy minus dr dy dz dx dA, and oh boy, sorry, let's group these together. We end up with double integral of minus, just I want to make this look as close to this as possible. So I'm going to factor out a minus from the two that have the derivatives and not from the other one, okay? So let's make sure that we have exactly what we need. We should have a minus dr dy, we do, so there's dr dy, and then it's going to be plus dq dz, so that's going to be a minus in here though, right? dq dz, that makes it a plus, and those are both times dz dx. Alright, so we just compare here dz dx. Those ones are factored out. Then we go over to dz dy, these two terms, but again, if we factor out a minus to make this look as close as possible to what we had before, then we're going to have the minus, so dp dz is now first, and minus dr dx, and this is dz dy. Okay, and so those are all gone, and then what's left over is this term that really reminds us of Green's theorem, right? This dq, this one we leave positive, right? So plus dq dx minus dp dy, this is all integrated up dA, and at this point we just compare with our formula from up above, and it turns out that it is exactly the same. And so under this very special case, which we made even specialer when we got to this point, right? But under this very special case, where our surface is given by the graph of a function over a domain in the xy plane, and that function has continuous second partial derivatives, then just by very, very carefully working out the two integrals on the two sides of Stokes' theorem, we were able to show that they have equal terms, right? All the terms are equal. So if you go back and you compare these, we get equal terms. And so in this very special case, we have shown that the double integral over S of the curl of f dotted with ds is equal to the path integral around the boundary of f dotted with dr. And this is Stokes' theorem proved in this special case. It holds in more general cases, but this is all we're going to prove for this course.